The next time I saw him, I was a starting graduate student at Harvard. I lived in this basement apartment on Everett Street near Mass Avenue. And when I was really tired, I would go, there was a drugstore on the corner, the old kind, that had this, you could sit down and have breakfast, a cup of coffee, not like the drugstores. You see them in the movies, right? You could walk in and have it. So I did that one morning, and Ken walked in at about, it must have been 8:30 in the morning, and he ordered an ice cream. And then he saw me, and, he hadn't, there was no reason for him to remember me from anything, He walked over, he said, "Hi, Ariel." I'd met him once 2 years before, and he said, "What are you thinking about?" So I had written this thesis, some of you might remember, on, it was a master's thesis, so probably you don't remember, on technological change, on diffusion of technologies. So we spent about 15 minutes, and I was with him for a while, and then just like you're always with Ken, he sort of knew more than you did, about the topic, and he just kept on going, and then at some point he had to leave, and he left. I felt rather stupid by the end of this, but then I learned later that no matter what conversation you picked up with Kenneth Ariel, I've seen him, he always knew more than everybody in the room, and it didn't matter who started the conversation. So over time, I've overcome that one, and okay, so that's it. He was, the other thing about Ken, by the way, you should know, and it's not so usual in our profession, he was the most humble person I think I've ever met. It was really an amazing person. Okay, enough on that. I'm going back. Okay, I'm going to talk to you about a paper with Uli Dorotzelski, who's at Penn, and Greg Lewis, who's at Microsoft. So let me give you some background. One goal of industrial organization, and maybe for some the most important goal, is to predict the response to a market of the market to a policy, say a merger or a tariff or an environmental change. Okay. So the way we've been doing it in I/O is pretty simple. We've been looking for a rest point, or Nash equilibrium, if you like, where each person is doing the best he can given what every other person is doing. Okay, and that we would look for that point. Okay. That makes some sense. If that's true, no person has an incentive to deviate because he's doing the best he can. There's no reason to change what he's doing. Okay? And if it's not true, if not every person is doing that, there's somebody who has a reason to deviate, okay, to change, and you would expect it not to persist. Okay? So the problem with, and we've made substantial progress that way, I think, I hope. On the other hand, it ignores two things. It ignores the transition period, and you might be interested in how you got, how long it takes to get to equilibrium, and indeed whether you will get to an equilibrium, okay? That's one thing, and that's the obvious thing. Probably the most important thing for industrial organization is maybe not that, but it's the fact that there are interacting agents in these markets. So there's firms that are competing with each other. If one firm produces product X, okay, it might be optimal for the other firm to produce product Y, and they're in Nash equilibrium. But if the first firm would have produced X prime, okay, the second firm might have been optimal to produce Y prime, okay, and they would be in another equilibrium. Okay, so this is called multiple equilibria. The issue is not so much an identification or estimation problem. We can typically look at the data and tell you what equilibrium you are in. Okay, we just read it off. We need some assumptions, but we read it off the data. But if you go back to our original goal, which is to do counterfactual analysis, so there's a merger or there's a tariff change, whatever you like, okay, I got to be able to predict where I go, and it's not in the data anymore because it's new, it's a counterfactual. Is that clear? And that's a real problem for I/O, okay? So this paper is an attempt to study transitions in an actual market setting, okay? I think it's the first paper that did that. There's a lot of experimental work where you sit people in a lab and you ask them to respond to changes. For those of us who have worked once in a while with a firm, you might not believe that a student is as complex and as understanding as the smartest guy in the firm. Okay, and this is sort of where we started. So I'm going to talk about that, and I'm going to try and do it all in pictures. Okay, so I usually use equations when I'm doing this. I'll try and do it all in pictures, so it should be easy to follow. That's the hope. Okay. And I'll show you that, in fact, in this market, we do transit to an equilibrium. Okay. But I'm going to then compare what would have happened if you would have done equilibrium analysis right away, okay, from the outset, or you followed a transition path. Okay. So the market is a real market. It's in the British electricity market. It's about frequency response. So frequency response is the frequency in the wires that go between places. If the frequency is too high, those wires blow up. Okay? If the frequency is too low, the wires sag down. Okay? So that's what frequency response is. There's a frequency response market in every electricity system. So Israel it doesn't work without one. Okay? It's not the main market. The main market is, depending on this country, in the UK, it balances a half hour before the right day. But what happens is, there's somebody's machine trips, okay? Somebody decides they want more air. It's air conditioning, the heat goes up, okay? And it doesn't quite balance, okay? And there has to be somebody who balances it, okay? The balancer is the person who owns the wires, okay? And his job, and one of the things he has to do is keep it within the frequency response within a pre-specified range. It's regulated, okay? So there's a law that says National Grid, which is the owner-operator in London, okay, has to keep the frequency within certain things, okay? Okay. So prior to November 1st, 2005, frequency response was done by fiat. Okay, what does that mean? It means National Grid had these things called governor controls. What governor controls do is they can take down any generator and move them around. Okay? And they can do it instantaneously. It's a supercomputer. Okay? You have one in Israel, I promise. Okay? And what they did is they just said, look, we can take you down whenever we want and put you up. It could be up or down whenever we want, and we're going to pay you this administrative fee, which was 1.7 pounds per kilowatt hour. Okay? On November 1st, 2005, the market was deregulated. We can talk about the history of this, but it's not necessary for the talk. Okay? It was deregulated. Firms bid in bids. Okay, and NG now bought the right to governor control your generators. Okay, and what I'm going to do, or what we did, is follow the market for 6 years after that. Okay, that's what the paper does. I'm going to try and do it in pictures. Okay, it's important to know that all these firms were there for many years before it was deregulated. Okay. So they knew a lot about cost conditions, okay? And they knew a lot about demand conditions and how they varied over time. Okay? Demand conditions really vary over time. There's Saturday, okay, there's summer holidays, there's Christmas, they vary over time, okay? Each generator submitted a separate bid, okay? It's important to know these details. So, I was talking to one of the students before, and the big difference between what we do here and what we do in trade is we focus on one industry and probably tell you more details than you want to know. So you're going to have to know some details to figure out what goes on in this industry, okay? There's separate bids for each generator. There's stations, and the stations have multiple generators typically, okay? And they're all the same. What does all the same mean? They use the same energy source, which is a major cost, okay? So they're coal, gas, or oil. There's some that are green, but they're not big, okay? And they're the same vintage. Higher vintages are more efficient. Older machines are more efficient. Younger machines, I guess, is more efficient, okay? Bids are submitted monthly, and they consist of a bid and a max. So it's not a pure auction, okay? Why is it not a pure auction? Because these guys are situated in different places, and there's different transmission constraints in different places. Is that clear? So it's not the same good you buy. It's close to the same good. It's electricity. But it's electricity in Lancaster, or it's electricity in London, okay? And also, these generators might be at the top of their, from the other market, they might be at the top of their place. They can't go higher, so you can only move them down, which ends up making them more costly and so on, okay? So and they have difference in reliability, okay? So it's not quite an auction. So the bids are submitted in the 20th of the prior month. Okay? So I know my competitor's bids this month. Okay? I don't know my competitor's bid next month as a simultaneous move auction. Okay? On the other hand, I don't know the quantities this month because it's not over and the quantities are published at the end of the month. Why do I tell you these details? Because the decisions they make can only be a function of the information they have at hand. And the information they have at hand don't include current quantities, do include current bids, but do also include the quantities in the past. Okay? Okay. Maybe I can use this. No, wrong way. Frequency response is costly, but there is no direct measure of the cost. Most of the cost is going up and down. If you go up and down many times, maintenance of the machines requires more maintenance. Okay. Okay. So that's the cost. It's implicit. The guys presumably know it. They've been playing this game for a long time, but I don't see it. Okay. NG pays bid times the time they're in the frequency response mode. So I put you in frequency response mode. Okay. Whether you you're called or not, you get paid. Okay. And if you are called, okay, you get the energy cost is reimbursed to you. So the only thing I'm going to worry about is the cost of the call. Okay. And this supercomputer does the allocations, which, by the way, the program was not changed over the time period that we checked. Okay. The bids are every month, so I bid at the beginning of the month, okay, for frequency response for the whole month. Okay. We have quantities that are by day. Okay. We know the market positions and the ownership structure. There are 130 of these generators. They're called balancing market units, and they're in 61 stations, and there are 29 firms. We're going to study the top 10 firms. Okay, which you'll see here. Okay, I'm going to come back to this, but I'll come back to this in a second. But these are the firms I'm going to study. So together they're about 85%, 83% of the market. Okay, it's not the whole market, and I will show you what we do to take care of the rest of the market. Can I go backwards? Yes. And the aggregate quantity is regulated. I already told you that. Whoops. So let me figure out what's going on here. Control minus. There we go. That should do it. Okay, these are the daily quantities. So you can see there's a lot of variance, but it's very common over time, and these are daily demand for frequency response. So now I got to do two things. The first thing I'm going to do is I have to tell you what else is happening in the environment. Okay, because what I want to do is separate out learning from other stuff. And if you don't know the other stuff, you won't be able to tell what's the difference between them. Okay? That's the first thing I'm going to do. And then the second thing I'm going to do is I'm going to give you an overview of just what happened in the data. And then I'm going to go to the learning models. Okay? Okay, so there were three kinds of things that changed over time in this market. How come I can't do this? Control negative. So this is the frequency response demand, or actually supply. And this is mandatory frequency response. In the middle of this is long-term contracts for frequency response. Okay, and you can see that in the middle of the third period, I'm going to divide into three periods. I should have said this. Okay, and you will see why in 1 second. Okay, so just bear with me for a second. Okay, in the middle of the third period, NG started writing longer-term contracts with. Okay, so that's a change. Not much happened in the first two periods, but in the middle of the third period it changed, okay? That's one thing that happened. The second thing that happened, again, the biggest input price is the source of energy, okay? And again, the three big ones are gas, oil, and coal, okay? And you can see there's movements in gas and oil prices and coal prices, not many in coal. But again, they're pretty stable until the last period. In the last period, both the gas and the oil price really increased sharply. Okay? Okay. And then the third thing that changed over the period, okay, is this is the number of active power stations. So some power stations always go down for maintenance. You have to go down for maintenance periodically, okay? But you can see that towards the third period again, a little less in the middle. Again, the number of power stations go up, okay? And in fact, this is the share of the always active power stations, and it goes down, okay? What do I want you to take from this? In the first two periods, everything was pretty stable, okay? In the third period, things started changing. Okay, so they're going to have to react to those changes, regardless of the learning model. Okay, in addition, if you like, to the learning model, they're going to have to react to those changes. Okay. Let me do this again. So you can actually read. I don't have to make it bigger. So this is not a big market. Okay, the big market is the balancing market, which is couple orders of magnitude larger than this. Okay, let me just say. There was deregulation of the balancing market. It was over by about 1996, but it happened in stages. It would have been very complex to analyze. They didn't want to give us the data. Okay? But you can see it's not huge. So Drax, which was the biggest station, made $100 million in the 600 million pound, 2011 pounds in this 6-year period. Okay? That's not large for these firms. But it is large enough for Drax as soon as they figured out. After the first few months, they figured out there was money in this market. They hired somebody to fix it. We talked to this guy, okay? So I know what happened, okay? So they did, and even if you go down to the smallest actor, it's over 2 million pounds a year. That's well enough money to hire somebody, okay, to handle this market. So it's not a huge market, but it's a big market, okay. So this is why we divide it into 3 periods, okay? What's going on in the first period? This is where the prices start. So the difference in blue and red in all of these things, red will be the unweighted average, and blue will be the weighted average. So the average price, if you like. The weighted average from the shares of the various firms times their bids. Okay? You can see what's going on. What's going on is it starts very low, and it goes up high. Okay? Until it reaches this point, and then the bubble bursts. Okay? The bubble bursts and prices keep coming down, and they come back rather dramatic. So this goes between 3 and I guess what is that? That's 7 or 8, okay? And then it goes down from 7, and it slowly goes down till it gets to about 5, okay? And then it just stays within 5 and 4.5 for the rest of the time. Why do I show you this? Well, many reasons, but one is it's the last part which looks stable. Is that clear? And it's the last part where things were changing in the environment. Okay? You should keep that in mind when we go on, okay? Now what I'm going to do is give you some pictures of what happened over time, and then I'm going to go to a model. Okay? Whoops. Okay, I'll give you the pictures one at a time. I'll just tell you what to take from the various pictures. This is the fraction of firms that changed their bid in the month. And at the start, it was 4 every 10, and then 3 out of every 10, and 3 out of 10. So that it started out much higher, okay? And then it decreased, but it never decreased in the third period. It was about the same as it was in the second period. These are the absolute values of the bid changes. Were there changes? Okay? So you can see the big changes occurred in the first period. Is that clear? The second period also had reasonably big changes, but not as big. And the third period, when the world was going crazy, different things were happening, they were very small changes. Okay? This is the actual variance in bids across agents. Okay, I'm going to get to a model, I promise. Okay? And you can see, it, in the first period, it goes way up, and then it starts coming down, and it sort of flattens out until the very end. And then I've got maybe 2 more pictures. This is an interesting one, because this is the within-firm variance. Remember, the firms have many stations. Okay? The stations are all facing exactly the same conditions. They have the same inputs. They have the same access to the transmission grid. Is that clear? So if you change one generator and keep the other ones constant, you're essentially doing a controlled experiment. Okay? So you can see there's a little bit of difference here because I also have generators in different stations that are owned by the same firm, but not much. Okay, and you can see that in the first period, there's a bunch of experimenting, and it goes down, actually hits 0 about here. experimenting stops. Okay? These are the actual bids of the 8 largest firms. So you can see that in the first period, what happens is, they're experimenting. They're changing their bids around. Okay? This is Drax. Drax found out slowly that if it increased its bid, it didn't decrease its quantity very much because it was in a position. 1 second, I'll get to you, I promise. Okay. It was in a position where there was nobody else that was as reliable as it. Okay. And it kept increasing its bid. Let me just finish this picture. Okay. So then what happens is up here, Drax is making a fortune, and these 2 other things start undercutting it, Peterhead and Barking. Okay. They keep undercutting each other, and the bid starts going down. There were some guys who just stayed low. Okay. Then Drax goes up. Okay. Holds its bid for exactly 1 period. Nobody follows, and it goes back down. Okay? So there were attempts to stabilize it at a higher price. And there was another attempt like this by Barking. You get to the 3rd period, okay? And in the 3rd period, you see there's very little differences in the bids compared to the other ones. They're not changing very much, okay? And this is a period when everything in the world is changing. Okay, now I'll take questions.
I think I'm a little bit confused. You said that they're experimenting, so within a firm you have different generators and they can place different bids for each
Yes.
generator. And the experiment is like how do others.
So you have a station. They're all located in a station. All the generators in a station are located exactly the same place. They have exactly the same access to the transmission grid, and they're exactly the same machines. Okay? So I have 2. Okay? I put one's price up. I keep the other one down. Okay? I get information on what happens if my price goes up by comparing what happens to the 2 of them. Okay? Somebody else. Reuven.
Does the regulator or the controller accept all the bids? Or
No,
what the higher bid means
Okay.
that you may not get
So
it?
subject to his transmission constraints and reliability constraints, these machines are differentially reliable. The supercomputer is programmed to minimum cost. Now it's not it can't do that exactly, so it does an approximation. Okay? But it's a pretty good approximation. That's what
But
it's
by
trying to
putting
do.
up a higher bid,
You get
you
lower quick.
risk not being,
Not being called.
not being.
That's right. That's the trade-off. Okay? Okay. I'm going ahead. So I'm going to kill all this. So the thing to remember is the probability of bid change was high in period 1, about the same in period 2 and period 3, and lower. The magnitude of the bid change has changed. In the first period, there was this huge interfirm variance, and then you got down to something that looked very much like the law of one price. One price for the various agents. Not quite, because they're not the same good, really. And then in the 3rd period, bids cycle in a narrow range. Okay, so now we're ready. We know what happened in the market, and we're ready to try and model it. Okay? It's not a very deep model. So why do I need a model? Okay, I need a model because what I want to do is analyze. This is as close as we get in I/O to a repeated game. Those of you who know what a repeated game, okay? It is essentially the same game. The only thing that's not repeated is the environment's changing over time. But it's the same actors bidding in the same market every year. Every month, sorry. Okay? And the environment's slowly changing over time. Okay. So what I want to do is I want to analyze the relationship between bids and the profits they make over time. Okay? Because that's the incentive to bid. Okay? So for that I need, and this is all the I/O students will know, I need a demand system and I need a cost system. Okay? Because profits are bids minus cost times the amount of quantity demand I get. I need to know what quantity demand they got and what was their perceptions of what they would have gotten. So demand I'm going to do just very quickly. I'll run over it. I'm going to just tell you what it looks like. How's that? It's the typical right-hand side. It's like a logit model. It's fully loaded in the sense of dummy variables for every month and dummy variables for every machine, and then bids and fraction of time partly loaded, and fraction that's firm frequency response with long-term contracts. Okay? And an AR1 disturbance. So that's all you need to know, really. These are the estimates. They make total sense. I'm not going to go through it. The omitted dummy is for being fully loaded, is for being out. And they don't want to call anybody who's out, who's on maintenance, okay? So what happens here is if you're fully loaded, it's better than being out, but it's not as good as being part loaded, because if you're part loaded, I can move you any way I want, so on, okay? And there is an AR1 disturbance. That's important because it tells me that I know something about next year's demand other than the observables from last year's demand, because it's a disturbance that's serially correlated, okay? This is what it looks like. So these are the red dots are our predictions. The black is the actual data. So most of the time when you do well on these things, it's because you get differences. You'll be getting differences between the various generators over time. So some generators get a lot and some generators don't get a lot. So here I'm giving you just the differences over time to show you we're actually fitting that reasonably well. So, Peter Phillips said this was a great fit, for whatever that means. Okay? So now I got to do the cost estimation. This is harder, okay? Because I don't see costs. I actually see demand, and I can run the demand system, okay? I see what everybody gets, okay? So, so I have to make some assumptions to go further here. Okay, so and I don't want to make total assumptions. I don't want to make equilibrium assumptions, okay? Because that's just doing what I'm trying to figure out, okay? So, so I'm going to assume only that I'm going to look only at the third period when things stabilized. And I'm going to assume that firms choose their bid to maximize their perceptions of expected profits. Their perceptions may not be realized, okay? But that they don't err on average. So over the last period, the third period, I think there's about 17 months. On average, they were right. Is that clear? So this rules out experimentation. It rules out collusion. There's good reasons to rule out collusion. Let me just show you. So collusive equilibria in I/O are a very simple thing, right? If prices are more than the Nash prices and the rest point prices, somebody has an incentive to deviate. That's the definition of Nash equilibrium, okay? So, and what a collusive price is, it's a price that's higher than the Nash prices. Somebody does have an incentive to deviate, but we're going to enforce it by some form of punishment scheme in the future. So if you deviate today, I will deviate tomorrow, and in the end, you're worse off than not deviating, okay? And in those types of frameworks, you expect firms to move prices up and down together, okay? Because there's going to be a price war, or there's not going to be a price war. We maintain the collusive agreement. We don't maintain the inclusive agreement. Okay. So this is the correlation between the bids from every two generators that aren't in the same firm, okay? And it's pretty much centered at zero. And you should expect, I expected a much stronger thing, because there's demand conditions that are going up and down in the summer and the winter that cause correlation. And if you look at the correlation between two generators in the same firm, it's always positive. Okay? So this is the thing that convinced me. There's several things in the paper that show that there's no collusion. Okay? But this is the one that convinced me. Okay. So how do I estimate a cost? So this is just what I said. This is bids minus cost. So that's the markup, if you like, on a unit of frequency response. And that's the amount of frequency response. Okay? So that's profits per unit of frequency response. That's the amount of frequency response. M is the market size. Sj is a share. Okay? And so what I'm going to do is I'm going to take my perceptions and maximize that conditional on the information at my disposal at the beginning of the period. Okay, which is this is that. Okay? What I want to say is two things here. What am I taking expectations over? What don't I know? Okay? What I don't know is the bids of my competitors. Okay, that's one thing I don't know. Okay? And the other thing I don't know is the parameters of the demand function. Okay? I'm going to assume I know my own cost because I've been playing this game for a long time. Okay? So what we're going to do is we're going to maximize that with respect to the vector of bids of each individual. There's a sum here because the firm owns many generators. Okay? So the sum is just over the generators the firm owns. And I'm going to find the bids for every period that maximize this. It's a vector for a given firm. It's a bunch of bids. Okay. And I'm going to set it equal to, I'm going to set the average equal to the optimal thing, which is a first order condition. And I get costs for every, generator. Okay? And just to give you an idea, if its average is 1.41, this is easy to see. What we think should be true is that generators that belong to the same firm should be approximately equally costly because they're all using the same source of energy and they're all same vintage, same everything, okay? And these are the within firm standard deviations. And you can see they're very small relative to the levels, okay? The other thing to note about this, so we were trying to convince ourselves that this is right, okay? The other thing to note about this is
The vintage is identical to
within a station.
within it.
Station, they're identical. They built it together, okay?
There were no additions over time.
No. Okay, and we have data on that, actually, okay? What was I going to say? Oh, yeah, the actual price pre-deregulation, the administered price was 1.7, which makes some sense because you would have to give them at least some markup for putting it in the market, okay? So it's pretty similar to what you might have expected, okay? And there are differences across cohorts and type of cost, and they're also consistent with what you would have expected. Okay. Here's the residuals from the first order condition, just to give you some idea of what's happening. So the first order condition should be 0 if they're maximizing and it's in Nash equilibrium, okay? Should average 0. Here's the average residual. You can see there's a difference here. This is 10,000, this is 3,000. So there's a difference in units, okay? And this is the variance and this is the mean. And you can see the residuals were much higher in the second period. They weren't getting it exactly right. Is that clear? And the variance was high. Whereas in the third period, the residuals, they're just moving around near 0. That's 0. Okay, they're just bumping around near 0, which means that that's what, if we're right, that's what they're supposed to be doing. In the third period, they're getting close to equilibrium. Okay? Okay. No name.
Essentially, they're playing against the computer. So they have to learn.
They're playing against the other actors
And the computer.
and the computer.
And they have to learn the computer, the program at the computer, and the other actors.
So the program from the computer is my demand system. That's what my demand system is. It's just taking the bids, taking what the computer does, and putting out the shares. Okay? So that's, when I said you had to learn about theta, that's learning the program about the computer. Okay? That's essentially what you're...
They don't know the program? They may not know what
They
consumers are going to demand, but
they don't know the program. The program's quite complicated. It's got transmission... Well, two things. Let me just say. No, wait, slow down. So what they need to learn is the response of the computer to a change in their bid. They've never bid before. Is that clear? They actually did hire people to do simulations of this. Okay? But the program is actually quite complicated. There's transmission constraints, there's all these things, and you'll see how quickly they learn it.
well, I would have thought the program is also responsive to consumer demand.
The program, this is frequency response. It is, a little bit, okay? But this is frequency response. Consumer demand mostly goes into what was done before in the half hour before and the long-term contracts. This is for something tripping, for a mistake being made, or it got cold all of a sudden, or it got hot all of a sudden, okay? So this is very, in the end, it comes from firms and consumers, okay? But it's very hard to predict, okay? It's all about, okay? That's what the balancing market's trying to do, to predict that. So this is things that weren't known when the balancing market, half hour before all this happened, okay? And this has to be true in every country. It has to have one of these things, okay? Good. I could quickly go over something that was sort of interesting to me, but I will do it very quickly, okay? You could ask the question, how badly did they do? They were making perceptions, changing their perceptions over time, changing their bids. You saw all these things changing around. You could ask the question, how badly did they do? Okay? Well, I can't tell you that exactly, but what I can tell you is an upper bound on how badly they did. What's the upper bound? I can say you knew what your say you knew the demand system, which I've estimated, I know it now, okay? And you knew what everybody else bid. Exactly. You could never do better than that, than maximizing that function. Is that clear? Okay. Okay. So, whoops, which way? Yeah, here we go, that's right. So this is how badly they did. They're very small numbers. These are percentages. Percentage change in profits. Had I bid exactly optimal from day one until the end, how would my profits have changed? Okay? And you get numbers, for the big guys, you get numbers like 2%, and then it gets down to 6%, 8% for one of the small guys. On the other hand, how much did my bid differ on average from the optimal bid, defined this way? Okay, defined, it's not really optimal because I couldn't do it, but if you could do it, how much does my bid vary? It's very large. 20%, 23%, 24%, so on, okay? So what's this saying? It's saying that the profit function is fairly flat on top. Is that clear? I move given what everybody else is doing, I move my bid 20%. Doesn't change profits that much. On the other hand, everybody doing that, you saw that the prices went way down and way up, okay? So there's an old article by Akerlof and Yellen on this, okay, which says, you know, it may be true that the profit functions are flat because it's a first order condition for the economists in the room, okay? On the other hand, it doesn't ensure that there aren't going to be very strong swings in prices, even if the environment is stable, okay? And that's what's going on here. The fact that the profit function is flat probably tells you something about the speed of learning. Okay, because it's going to be hard to learn if I move my bid a lot and nothing much happens. Okay. Okay, now I'm back to learning. Now I have 20 minutes to tell you quickly what happens in the learning models. Okay. So let me just say, in period one, if you remember the pictures, there was heterogeneous behavior, a bunch of experimentation, and we don't have a model for either. Okay, so let me tell you, I've asked many of my theory colleagues this. Is there a model with experimentation and agents interacting? The best answer I got was from Steve Morris, who said, yes, there are models like this, but you'd never want to use one. So we didn't do it, okay? And I'm just going to skip the first period, okay? And I'm going to look at the second and the third period, okay? And I got asked the question, what are we learning about? Okay? So the things that I'm unlikely, so I'm going to assume I know my costs and I know the primitives. Okay, I've been playing this game for a long time. I know the variance in demand. I know the probability of going down for maintenance, stuff like that. It's not one-to-one. It's a probability distribution. I'm going to assume you know the probability distribution. Okay, and I'm going to assume you know the firm fixed effects, which are essentially the reliability of the generator. Okay, what I really don't know is other firms' bids. I've never seen a firm bid before. I don't know what my competitors are going to do. Okay? And I don't know, this is what I was explaining before, I don't know what this computer is going to do when I change my bid. I don't know the response of price to bids. Okay, I might not know other things either. It work out that that doesn't matter, but it's possible and I'll show you that. Okay. So, you know, there's an amazing there's not much in the literature about learning. Okay. Again, the only thing that I know of in learning are these experiments. There's nothing on real data, as far as I can tell. Okay. So we're going to use variants of a theoretical model called fictitious play, which the theorist will know about. So it just goes something like this. There's been bids, a whole vector of bids from every generated from every firm over past periods. Okay. And what I'm going to assume is the probability distribution of bids today are a geometric weighted average of the bids that were made in the past. This is a variant of fictitious play. Okay, and I'm going to estimate the parameter that tells me, you know, how they decay. Okay? So I'm going to show you results for delta equals 1. So that's equal weights for every past period. Okay? Delta equals 0 is what's known as best response. I only pay attention to the last period, what the guy did the last period. And delta equal 0.5 is in the middle. We actually estimated a maximum likelihood estimate. I'll show you that too, but its variance was pretty broad. Okay. So that's what I'm going to do about fictitious play. I still have to learn about the demand system. Okay, that's the other thing I have to learn about. So we're going to borrow this from the macro guys. okay, who did adaptive learning. So what's adaptive learning? It's actually the most simple thing you can possibly think of. You use all the data you had until today, you estimate a demand system, and you use those estimates as a prediction of the demand system tomorrow. Is that clear? Okay. So every period you're getting better and better at estimating the demand system because there's more and more information available to do that. Okay. So there's papers on this by Sargent and Hansen and all those guys. Okay. Okay, and then I'm going to show you results for an equilibrium model, which I should have to tell you how I calculate yet. And every the learning model about bits for different delta, and then the learning model about the parameters of the demand system. I'm going to show you ones for just learning about alpha. Alpha is a parameter of bids. It's the bid reaction of the demand function. Okay, and then these are the month fixed effects, and these are other things. These are the parameters of the things that change over time. Okay, so I'm going to just show you all of just results for all of them. Okay, and you can pick out what you like. Okay, there's going to be an obvious answer. The other thing is, remember what I started with is what I wanted to do is compare to Nash equilibrium because that's what everybody does. Okay, so I have to also compute a Nash equilibrium. Okay, so the Nash equilibrium, in the Nash equilibrium, what happens in a Nash equilibrium is, you know, I don't know what my competitor is going to do, but I know the distribution of his bids because I know the primitives generating randomness in the system. Okay, so what I do is I take my bid. My bid is the optimal bid, given my perceptions of what everybody else does, and theirs is optimal given mine. What do I get for perception? The perceptions has to be the true thing. Okay, the true distribution of everybody else's bids. Okay, this is actually reasonably complicated to calculate. Okay, but it's a fixed point, and we calculated it. Okay, so that's it. Okay. Okay. So now I have to give you measures of predictive accuracy. Okay, now I'm going to play a horse race, essentially. I never do this, by the way, but this is a paper. This first paper I've ever done anything like this. Okay. I'm going to give you a measure of predictive accuracy. I'm going to give you two measures of predictive accuracy. Okay. The first measure is the share-weighted difference in the average bid predicted by the model minus what actually happened. Okay. So why are we interested in this? This would be NG's cost. So if National Grid was trying to predict its cost, and it used this to predict, is that clear? And in a given period, this would be its error, and then we're just taking the absolute value of that. Okay? So that's relevant for National Grid. And then the second one is just the share weight. It's the typical mean square error calculation, the square error of the prediction, okay, and weighted by the shares of the people again. Okay? And I'm going to do this twice. I'm going to do it once for one period ahead prediction. And then I'm going to do it once for the whole, for the whole second period and once for the whole third period. Okay? And how you do that is you use the prediction. So if I'm going to year 2, I use a prediction for year 1 as last year 2, as the thing I'm conditioning on in year 2. Okay? And you just iterate. Okay, that's it. So let me start with the demand parameters. You should have expected this from the picture. So I should ask the I/O guys, how well you think we estimate the demand parameters and how quickly we get them. I mean, this is just adaptive learning. So it's just a question of how I increase my data availability. Okay. How quickly do I learn the parameter? That's the question. Okay. I won't do this. I won't embarrass anybody. The answer is the reason you learn it very quickly. The reason you learn it very quickly is because they're experimenting in the beginning. Is that clear? So there's huge variance in prices, and you nail the demand system right away. So by the time the second period starts, you're within 2% of the final number in the demand system. Okay, that's a difference, and you're going to see it matters, but it's not huge. Okay, and if you look at it, this is the picture. This is when you just estimate the demand parameter, and you assume you know all the other parameters. It's going to work out that that's what seems like people are doing. Okay, they act as if they knew the other parameters. Well, they played this game many times before. It's the monthly mean, and they've been playing this over these months for many times before, and whether they were fully loaded or not fully loaded. And they've been playing this game many times before. Okay? And I'm not going to go over the other ones, but you'll see in a second that that's the one you want. Okay. So now the predictions. Now I'm going to give you the predictions. I'm actually going to make this. I skipped a bunch, but it's good. These are the predictions for the middle period. So the middle period, remember, prices are going up. There's a bubble. The bubble breaks, and people start coming down. Okay? And these are the predictions for that period. Okay? I'm just going to show you without going through this. I should maybe make this bigger. So this is just the prediction for NG's monthly cost. Okay? You can see here, okay, that what's doing best is either you know all the either its best response, or you know something. What's happening clearly is you're weighting bids that were there last period more than bids that were there 2 periods ago and 3 periods ago and 4 periods ago. That ends up being very important. You can see the difference between f of 1 and f of 0 or f of 0.5. Works out that we estimated f also by maximum likelihood. You got a number of 0.3, but the standard error probably didn't, 0 and 0.5 were within 2 standard errors. So I don't want to say we know the number. Okay? It matters a little bit if you let them estimate A, the alpha coefficient. Okay? It matters much more, of course, if you iterate. A little error gets, when you do the sequential prediction for 5 periods, a little error gets magnified a bit. The thing that's really interesting is if you do equilibrium, you do really bad. Okay, you do 60% worse, okay, than you would have done if you took one of the learning models. Okay, I had no, finger in this game. I've never written down a learning model in my life. Okay, this is just what the data are saying. Okay, and if you went, let me see. I think I have to. If you did the mean square error thing, predictions for middle period. Guess it's next page. Yeah, there it is. Whoa. Sorry. Here's the mean square error. This is the mean square error for the second period. You get exactly the same thing. Okay. What you know is it should be in this corner. Okay, it's somewhere between f of 0 and f of 0.5. You like A alpha. You like estimating alpha better than, you do better by assuming they're learning about alpha than they knew alpha. A little better. You do quite a bit better if you go to the multi-period predictions because it accentuates the error. Okay, and you do a lot better than Nash equilibrium. Okay, and this is already, we're now 2 years into this thing, but it's monthly predictions, so there's not many predictions, but you're into it quite a ways. Okay. So I'm going to now compare this to the Nash equilibrium. So this is. You can ask, are they significantly different? So just take the cost that's predicted by the model minus the cost predicted by the equilibrium and see if they're different. Just do a linear regression, okay? So if you just put in a constant term, they are different. And then you see what's going on, which is if you put in a time trend, they are way different at the beginning of the second period. And it's slowly converging to being close to each other. Is that clear? That's the same thing that's happening to the mean square error. Okay, it starts out very different, and by the end of the second period, it's getting much closer. You can see what's going on in a picture. So this picture, the top one is the actual data. The dark black one is data. It's the average. I'm now doing the cost to NG because it's just one number. It's easy to see. Okay, this is the equilibrium. This is the one-shot prediction, 1 period ahead prediction, and this is the multi-period prediction. Okay? So you can see what's going on. What happens is equilibrium drops right away, almost, to where we get to at the end of the third period. And the data isn't like that. The data doesn't get there right away. It's going down slowly. Okay? It does get there, and by the end of the second period, they're almost the same. Is that clear? But they do get there. Okay, so now let's move on to the third period. And here's the same picture for the third period. Okay, the same tables for the third period. Okay, and now, again, A0 and A alpha are almost exactly identical by the third period. There is a difference. I mean, remember, this is equilibrium. Okay, I don't get to choose a parameter to make it fit better in the equilibrium. It's just whatever was there, okay? Here we actually get to choose a parameter. Okay, we get to choose this learning parameter, delta, to do it well. Okay, and you can see it's much closer in the third period. Okay, but we still do slightly better. The learning model still does slightly better. Here you can see that if you look back, and I'm not going to do this again because my control over the machine isn't great, but this is 1/3 of the mean square error in the prior period. So in the third period, you've really decreased the mean square error quite a bit. Okay, you're quite near it. Okay, and if you do the regressions now, they're marginally significant. They're almost the same. Okay, between the equilibrium model, okay, and the best fitting learning model. Is that clear? And you can see that also here. Okay, this is again, the black line is again the data. The red line is the equilibrium, and the blue line is our predictions from our best fitting model. And you can see what's really happening is they seem to be predicting each other. The blue line and the red line seem to be predicting each other, and they're pretty close to the Nash equilibrium. Why do I emphasize this? Okay, it took some time to learn how other people were going to bid and to learn what the parameters of the band system were. Okay, and there was a real transition. Okay, it took 4 years, about 4 years altogether. So that's only 48 bits, but it is 4 years. Okay. On the other hand, once we got there, and things changed, and in the last period I showed you at the beginning, all this stuff changed, right? The oil and gas price went through the roof. Okay, we started having new entry. By the way, most of the new entry was green, was solar and wind power. Okay, because they gave stuff for solar and wind power. Okay, all this stuff was changing in the last period. But once they knew approximately how their competitors bid, they could adjust quite quickly. Okay, there are differences here, but they're minor compared to the differences before. Okay, the big issue was learning how my competitors bid and learning how the computer responded to these price movements. Okay, so this is the end, and all I have to do is overview. Okay, so again, there was this initial phase with heterogeneous responses and experimentation that we really just don't know how to analyze. And if a theory colleague would tell me how to do this, I would do it. Okay, because it's interacting agent model, so I can experiment for many different reasons, including learning what my competitors will do, okay, by experimenting, okay? This was followed by a second phase in which there was a distinct movement towards a set of policies which satisfied all the conditions of equilibrium, okay? And the transition lasted 2.5 years. Okay, it was a significant transition, okay? The final period, despite all these environmental changes, the final period, they could track it. They were a little bit of lag if you would have looked at those things closely. They tracked it maybe a year afterwards, but they could respond very quickly to the changes in the environment in the last period. Okay? So it suggests, I would like to say something that I won't say. It suggests that, that if the learning part that we have to do is learning, and is really, we should be focusing on how firms perceive their competitors to act when the environment changes. Okay? That's what's going on, and maybe the demand system and things like that. You might have to learn that also in the environment. If you were in an environment where the demand was reasonably stable, which is most of the time that we are in I/O, but something changed, there was a merger, okay, which changed bidding structure, you'd be focused on how they respond to the bidding thing. What I would like to be able to tell you is if you do fictitious play, okay, you'll get to the new equilibrium. But we fit the fictitious play model so that it would get to the new equilibrium, okay? So I'm not sure, and you also saw in the middle that it wasn't a pure fictitious play model. Firms were reacting to each other. Remember, DRAX went up, nobody followed, went back down. There was a bunch of that going on. So it doesn't fit perfectly, and there's a lot more to do. But this is our attempt to start on this problem. That's it. I'm happy to take questions.